So what if I told you that you are not using your GPU and your GPU is actually sitting idle for 40% of your time that you are running the code. You have spent thousands of dollars on a card, but because of few missing lines of CPP, you are essentially using a GPU from three generations ago. Uh, Same kernel, same data, same hardware. Yet, the version on the right finishes twice as fast as yours. We aren't hacking any assembly language. We are not even overclocking. We are just changing the way we talk to the hardware. In the next few minutes, I'm going to show you the architectural secret that separates a senior AI engineer from everybody else. That is CUDA Streams. Now, let's try to understand using a real world example. Imagine you own a restaurant and you have world class chef who can start cooking or chop onions or chop hundreds of onions in a minute or even in 1 second. But your chef or our GPU refuses to start until the entire load of 1,000 onions is moved from the truck to the kitchen. So in a standard program, this is what happens. Your PCLE bus, the truck, unloads data to the GPU memory. The chef sits there and watching. Then once the truck is empty, the chef starts cooking. But during that time, the PCLE bus or the truck driver stays and waits till the chef completes the cooking to move the data. And this is synchronous execution. It's the default way of doing things, and its performance is a very poor and it's a performance killer. To reach the maximum minutes of efficiency, we need to make sure that both the chef, that is the GPU, and the PCLE bus are working at the exact same time so that we get the maximum efficiency and the maximum performance out of our GPU. So here we have the function that is used to run the kernel for identifying the square of elements in a particular array. And this is the kernel that we have written to find the square of the element in an array. And this is the function that we are using to call the kernel. And here you can see that first you are copying the data from the host to device, then we are calling the kernel, then we are copying the results from the host to device. And from the flow of the code itself, you can understand that each line needs to wait for the previous line to complete the execution. For example, here we are expecting that the cudaMemcpy copies the data from the device to host or host to device so that we can start the execution of the square kernel. And since we have almost 16 million of data with us, it takes too many seconds. That is unnecessary if we are using CUDA Streams. Now let's introduce streams into our execution. A stream is just a sequence of operations that are executed in an order. But here is the magic. Different stream can execute their own operations simultaneously. Now let's look back into the previous example that we already discussed. There, the chef used to wait for the truck loader to unload all 1,000 units of onions so that he can start cooking. Now let's change it a bit. The truck load unloads the hundreds of onions out of the 1,000 ones, and the chef starts cooking. In the meantime, instead of waiting at the parking lot, our truck driver goes back and fetches the next load so that the chef is ready with the next set of onions to continue the cooking. And this process iterates so that the copying and execution does not take separate time. It can be executed simultaneously. So here we can divide, for example, here we can divide the 16 million data into 4 streams, and when the stream 1 is being executed, we can copy the data from stream 2 to the device so that stream 1 and stream 2 works parallelly and independent of each other. And this keeps our PCLE bus really busy and our GPU core busy, and we will achieve the hardware saturation. So this is where the 90% of the developers fail and where things get messy. They write the stream code, but it does not get any faster. But why? That is because of the pageable memory. Your standard RAM is really messy. The OS moves it around. The GPU cannot safely grab it. So the CPU has to first copy your data into a pinned, a non-movable staging area before sending it to the GPU. So if you are not using cudaMallocHost, your asynchronous copies are actually failed. The CPU will block while it moves data to the staging area. You must pin your memory to unlock true concurrency. This is the difference between a tutorial that works and a system that scales. Now let's observe how we have implemented the multi-stream code for the same. And here you can observe that we are using the same kernel to find the square of the element. You can see that. And as you can see, we are using the same kernel. And we have, like I said, 60 million data. And here we are dividing them into streams of 4. So we have streams of 4 streams containing 16 by 4 elements. And we are copying these elements inside a loop. And we are indexing the elements based on the stream ID. So here we are first copying stream 0, for example, and then once the stream 0's execution start, we copy the stream 1. And when stream 0 is being copied from the host device to the host, stream 1 is being executed and stream 2 is being copied. And this makes sure that our code doesn't make sure that both the GPU and the PCLE bus is busy the whole time. So the little variable streams I is used to indicate the index of the particular stream that we are processing at that moment. And this is being added as the 4th element in the kernel as well, so that we can identify and copy and execute the correct streams at the right moment. And this makes sure that everything works perfectly and each stream works perfectly independent of each other, and nothing happening on stream 0 does not affect something happening in the stream 1. So once you run this particular executable, we get almost 15 millisecond for single stream and 8 millisecond or close to 10 millisecond for multi-stream, and that is 1.5x times the faster than the single stream, and that is using my RTX 4050, and that is a low end or mid-range graphics card. And you can imagine this is working on only 16 million data, and you can think how we can scale this much further using multiple streams and higher amount of data. And on a real world workload like a video transcriber or a neural network data loader, this is the difference between 30 fps and 60 fps. Learning CUDA is not just about learning the syntax, it's about how the data flows through the silicon, either within the GPU, from the device to the host, and host to device. So everywhere there is some optimization that needs to make sure our code is working perfectly fine without breaking even the syntax as well. This is what happens when you try to learn CUDA. And if you find this breakdown helpful, you are the kind of people that I want to visit in my channel, or I want in this channel. So no shortcuts, no hypes, just real engineering. If you want source code or anything, I will pin down in the description below. You can just check it deep below. And you can also use Nsight to visualize this. And I have a copy or a screenshot with me. I will also share it in the video as well. So what do you feel? Should I optimize something else, or should I work on a different project? Let me know in the comments below. I will see you in the next video. Bye.